Welcome to Bewitching Brain. My name is Sophia Mazzacchio, and I am an MD candidate at the Medical College of Wisconsin. I am super interested in the brain and nervous system as a whole. At the Medical College of Wisconsin, the Student Interest Group in Neurology provides educational outreach and is always looking for ways to engage community as we learn more about the bewitching brain. Please subscribe, share, and email me, or comment below with ideas or questions. Take good care, be safe, and help others be safe. In this week's video, we will elaborate on the resting membrane potential and begin discussing how neurons alter it to signal. So to begin, we're going to review a major concept that will help us understand the resting membrane potential. A concentration gradient is simply a difference in the amount of some substance from one side of a barrier to another. If the barrier is impermeable to that substance, it will not cross. However, if the barrier is permeable, then the substance will cross and eventually there will be approximately equal amounts of the substance on either side. The original setup is called a concentration gradient. There's a higher concentration of the substance on the right side on this diagram than on the left side. Substances naturally move down their concentration gradient from high to low concentration if they are able to. Okay, so let's start with the basics about the resting membrane potential. The resting membrane potential is a charge difference between the inside and outside of the cell membrane. It is a relative difference, such that the inside is more negative relative to the outside. The neuron resting membrane potential is roughly around negative 70 millivolts. Here we have a simplified drawing of a cell. The black circle represents the cell membrane. It is difficult to depict in a large-scale drawing, but the relative charge difference is only maintained just on either side of the membrane. It is not the cell as a whole that is more negative compared to the outside. Now let's zoom in on the membrane to see how the resting membrane potential is created and maintained. For orientation, here is the phospholipid bilayer with phosphate heads in blue and simplified lipid tails in black. You can see the outside or extracellular part and the inside, which has the cytoplasm. Okay, so there are two primary ways in which the resting membrane potential is created. The first way is by the presence of organic anions inside the cell. Because the cell membrane is impermeable to organic anions, because they are large and negatively charged, they remain inside of the cell. This creates a negative charge inside of the cell membrane relative to the outside. The second way in which the resting membrane potential is created is by sodium and potassium ion channels. The ion channels that contribute to the resting membrane potential are leak channels. They are open at resting membrane potential and they allow sodium and potassium ions to move through them passively, just like the barrel we talked about last week. In this diagram, we have one sodium channel and one potassium channel. There is more sodium on the outside of the cell compared to the inside. This means that sodium will tend to flow through the channel to the inside of the cell down its concentration gradient. Conversely, there is more potassium on the inside of the cell membrane than on the outside. This means that potassium will tend to flow through the channel to the outside of the cell. Every time a sodium ion comes into the cell through a sodium channel, the inside of the cell membrane becomes more positive by 1 charge. Conversely, every time a potassium ion leaves the cell through a potassium channel, the inside of the cell membrane becomes more negative by 1 charge. So you might be thinking, then why don't these channels just cancel each other out? The answer is that there are many more potassium channels than sodium channels within the cell membrane. This means that more potassium leaves the cell than sodium enters the cell. Therefore, the inside of the cell membrane becomes more negative relative to the outside. If the membrane had only potassium channels, the resting membrane potential would be somewhat more negative, perhaps 20 millivolts more negative. The presence of some sodium channels prevents this from occurring. In this video, we will not get into the details of the electrochemical gradient and Nernst potentials. If you would like to understand these concepts and therefore have a more detailed understanding of the resting membrane potential, please comment or contact me and I can provide you with helpful resources. The resting membrane potential is maintained through a combination of the continued presence of organic ions, flow of ions through the leak channels, and sodium-potassium pumps. Sodium-potassium pumps move sodium and potassium ions against their concentration gradients. This helps maintain the higher concentration of potassium inside of the cell and the higher concentration of sodium outside of the cell by opposing the leak channels. In this diagram, you can see 2 sodium ions leaving the cell and 3 potassium ions coming into the cell. So let's get back to neurons. Neurons utilize changes in the membrane potential in order to signal. Depolarization is a positive shift in the membrane potential. For example, the membrane potential might go from negative 70 millivolts to positive 20 millivolts. Hyperpolarization is a negative shift in the membrane potential. For example, the membrane potential might go from negative 70 millivolts to negative 90 millivolts. We will discuss how this occurs in greater detail in future videos. With that, there will be no new videos for a couple weeks due to personal commitments and final exams. Do feel free to comment and contact me with any questions or suggestions. When we return, we'll be discussing signaling in neurons, as well as some disorders involving neurons. Thanks for listening, Brainiacs, and tune in soon for more.